It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
Think about your morning commute. You pull up your map app, type in your destination, and in seconds it gives you the best route. It dodges traffic, accounts for road closures. But have you ever stopped to wonder how? How does a machine solve a problem that involves billions of possible turns and roads? This isn't just about maps. It's about how a character in a video game finds you, how a data packet zips across the internet to load this podcast, or how a warehouse robot plans its path to grab your order. This is the world of AI search algorithms, the invisible intelligence that constantly finds the optimal path through a maze of possibilities. Today, on AI Deconstructed, we're going on a journey. We'll start by fumbling around in the dark with algorithms that are powerful but blind. Then we'll give them a spark of intuition, a kind of digital compass called a heuristic. And finally, we'll combine these ideas to build one of the most elegant and influential algorithms ever created, A*. We'll even meet the wobbly, trailblazing robot that started it all. Before an AI can search intelligently, we need to understand what it means to search without any intelligence at all. This is called uninformed search, or more bluntly, blind search. These algorithms operate with only the problem definition, a map of all possible locations or states and the connections between them, and nothing else. They have no additional knowledge to guide them toward the goal. Imagine you're placed in a massive pitch-black hedge maze. Your goal is to find the exit, but you have no clues about where it is. What do? You can't just wander randomly. You need a systematic strategy to guarantee you eventually find a way out. One such strategy is to explore methodically, layer by layer. You check every path that's one turn away from the start. Then you check every path that's 2 turns away, and so on. This is breadth first search, or BFS, which we introduced in our last episode. It's like dropping a stone in a pond. The ripples expand outwards evenly, exploring all nodes at a given depth before moving to the next level. The great thing about BFS is that it's complete. It's guaranteed to find a solution if one exists. It's also optimal in the sense that it will find the path with the fewest steps, because it explores the shortest paths first. But this thoroughness comes at a steep price: memory. To check all paths of length 5, BFS has to remember every single path of length 4. Its space complexity is exponential, growing as big O of b to the power of d+1, where b is the branching factor, and d is the depth of the solution. In a large maze, or any complex problem, it will quickly exhaust available memory. This fundamental tension between finding the best solution and the resources required to do so is a recurring theme in computer science. It creates a clear need for a more efficient approach. Another strategy we discussed is to pick one path and follow it as deep as you can. If you hit a dead end, you backtrack to your last choice point and try a different turn. This is depth-first search, or DFS. In our maze analogy, this is like keeping one hand on the left wall and just following it wherever it leads. DFS is the mirror image of BFS in many ways. It's incredibly memory efficient because it only needs to remember the single path it's currently on. But it sacrifices optimality. It might stumble down a ridiculously long, winding path and find an exit, completely missing a much shorter path right near the entrance. It finds a solution, not necessarily the best solution. So, our blind searchers can get the job done, but they're inefficient. BFS is a memory hog, and DFS is a wanderer. They are brute force methods, systematically exploring every possibility without any preference for promising paths. To do better, our searcher needs a clue. It needs a sense of direction. This is where the AI really starts to kick in. Informed search algorithms are given extra knowledge to work with. They have a guide, a rule of thumb, an educated guess that helps them prioritize more promising paths over less promising ones. In computer science, this guide is called a heuristic. The word itself comes from the Greek heuriskane, meaning to find or to discover, the same root as eureka. A heuristic function, often written as h of n, takes a state, your current position n, and returns an estimate of the cost to reach the goal from there. It's an intelligent shortcut designed to solve problems more quickly when classic exhaustive methods are too slow. Let's go back to our maze. What if you could hear the faint sound of a party at the exit, or you knew the exit was generally to the north? You'd naturally start exploring paths that take you closer to the sound or further north. That clue, the sound, the direction, is your heuristic function. It doesn't guarantee the path is clear, but it's a smart bet. For a pathfinding problem on a 2D map, our heuristic h of n is often one of two types. If we can move in any direction, like in the real world, we use the Euclidean distance, the simple straight-line distance, which you'll remember from geometry as the square root of the sum of x2 minus zone squared and ytwo minus yon squared. If we're on a grid where we can only move up, down, left, or right, like in many video games or a city grid, we use the Manhattan distance. This is named after the grid-like streets of Manhattan. It's simply the distance in x plus the distance in y, or the absolute value of x2 minus zone plus the absolute value of ytwo minus yon. It's the number of horizontal and vertical squares you must cross to reach the goal. The key word for any heuristic is estimate. The straight-line distance heuristic doesn't know about a river or a building in the way. The Manhattan distance heuristic doesn't know about a wall of obstacles. It's just an optimistic straight-line guess. The quality of this guess will directly determine the efficiency of our search. A terrible heuristic like h of n equals 0 for all nodes provides no information, and our informed search just degrades back into a blind one. A perfect heuristic would tell us the exact cost, and we'd just march straight to the goal. The reality, and the art of this, is in finding a heuristic that is good enough. The most straightforward way to use a heuristic is to be greedy. At every intersection, you choose the path that seems to take you closest to your goal, according to your heuristic, and ignore everything else. This algorithm is aptly named Greedy Best First Search. Its decision-making formula is as simple as it gets. The evaluation function f of n is just equal to the heuristic function h of n. It completely ignores the distance you've already traveled to get to your current spot. To understand the pitfall here, imagine a tourist in Paris who wants to get to the Eiffel Tower. A greedy algorithm would have them walk in a straight line towards the tower at all times. This might seem fast, but it could lead them straight into a building, or to the bank of the River Seine with no bridge in sight. They are so focused on the goal's direction that they ignore the actual path, potentially taking a much longer and more difficult route just to maintain that straight line heading. And that's the critical flaw of greed. Greedy search is often very fast and memory efficient because it aggressively prunes the search space, focusing only on what looks best right now. However, it is not optimal and not complete. It can get stuck in loops or follow a promising-looking path to a dead end. This single-minded focus on the future, the h of n, without acknowledging the cost of the past, leads to poor decisions. We have a fast algorithm, but we can't trust its answers. We need to temper that greedy ambition with a dose of reality. This leaves us in a bit of a pickle. We have two different approaches, both from our curriculum. On one hand, we have uniform cost search, or UCS. It's essentially breadth-first search, but for weighted graphs where edges or paths have different costs. UCS is the opposite of greedy search. It only cares about the past. It always expands the node on the frontier with the lowest total cost from the start. It is meticulous, careful, and guaranteed to be optimal. But it's also blind. It has no sense of direction. It's our tourist from the start, carefully exploring every one-cost street, then every two-cost street, and so on, still very, very slow. On the other hand, we have greedy best first search. It only cares about the future, the heuristic H of N. It's fast, it's guided, but it's not optimal and easily fooled. So, we have one algorithm that's optimal but stupid, and another that's smart but wrong. We need to find a better way. To do that, we have to go back in time, to the late 1960s at the Stanford Research Institute, or SRI. Researchers there were building the world's first mobile robot that could perceive and reason about its own actions. It was a tall, wheeled contraption with a TV camera for an eye, and because it wobbled as it moved, they nicknamed it Shaky. Shaky, developed between 1966 and 1972, had to navigate rooms filled with large blocks, planning its own routes to complete tasks like push the block from room A to room B. The simple search algorithms of the day weren't good enough. The researchers, led by Charles Rosen and including AI pioneer Nils Nielsen, needed something smarter. Out of this practical need for a robot to find its way, the S-star algorithm was born. The genius of S-star is captured in one elegant equation. F of n equals g of n plus h of n. It looks simple, but it represents a profound balance between two competing ideas. First is g of n, the cost of the past. This is the Dijkstra's algorithm part of S-star. It represents the exact known cost of the path from the starting point to our current node, n. This is the reality of the journey so far, the wisdom of experience. Second is h of n, the guess about the future. This is the greedy part. It's the heuristic function, the estimated cost from our current node n to the goal. This is our intelligent foresight. Finally, f of n is the balanced decision. S-star combines them. At every step, it chooses to explore the node with the lowest f of n score. It's not just the node closest to the start, and it's not just the one that looks closest to the end. It's the node with the best combination of a cheap path so far and a promising future. This dual-pronged evaluation prevents the algorithm from falling into the traps that plague its predecessors, creating a search that is both directed and robust. Let's see this in action with a verbal walkthrough. Imagine a simple 3x3 grid. Our start is at the bottom left, coordinates 0, 0. Our goal is the top right, 2, 2. To make it interesting, there's an impassable wall at the center square, 1, 1. We'll say that moving straight, up, down, left, or right costs 10 points, and moving diagonally costs 14. To guide us, we'll use a simple heuristic called the Manhattan distance. It's named after the grid-like street layout of Manhattan and simply counts the number of horizontal and vertical squares to the goal, ignoring obstacles. Our h of n will be the number of horizontal steps plus vertical steps to the goal, multiplied by 10. S-star uses two lists to keep track of its progress. An open list for nodes it has seen but hasn't fully explored, and a closed list for nodes it's finished with. Step 1. We start at 0, 0. The cost to get here, g, is 0. The heuristic cost, h, is the quantity, absolute value of 2 minus 0, plus the absolute value of 2 minus 0, all times 10, which equals 40. So its total score, f, is 0 plus 40 equals 40. We add the start node to our open list. Step 2. We pull the node with the lowest f score from the open list. Right now, that's just our start node, 0, 0. We move it to the closed list and look at its neighbors, 0, 1, ona 0, and the diagonal 1, 1. But wait, 1, 1 is a wall, so we ignore it completely. Step 3. Let's evaluate the neighbor at ona 0. Its parent is the start node. The cost to get here G is 10, one straight move. Its heuristic H is the quantity, absolute value of 2 minus 1, plus the absolute value of 2 minus 0, all times 10, which is 30. So its F-score is 10 plus 30 equals 40. We add ONA 0 to the open list. We do the same for the neighbor at 0, 1, and it also has a G cost of 10 and an H cost of 30, for a total F-score of 40. Step 4. Our open list now has two nodes, ONA 0 and 0, 1, both with an F-score of 40. Let's just pick ONA 0 to explore next. We move it to the closed list. We look at its neighbors. One of them is 0, 1, which is already on our open list. This is a key moment. We must check if this new path to 0, 1, going through ONA 0, is better than the old one. The new G cost would be 10, to get to ONA 0 plus 14 for a diagonal move, totaling 24. The original G cost for 0, 1 was just 10. Since 24 is not less than 10, this new path is worse, so we ignore it and leave 0, 1 as it is. We then calculate the scores for any new neighbors and add them to the open list. The algorithm continues this simple process, always picking the node with the lowest F-score from the open list, moving it to the closed list and evaluating its neighbors, until it pulls the goal node off the list. The final path is then found by following the chain of parents back from the goal all the way to the start. Let's quickly contrast this with what our other algorithms would have done on this same 3x3 grid. Breadth-first search, exploring layer by layer, would have pointlessly explored 0, 1 and ONA 0, and then expanded outward from them, wasting time exploring nodes away from the goal before ever getting around the wall. Depth-first search is a gamble. It might have picked the path 0, 1 to 0, 2 to 1, 2 to 2, 2, and found a good path quickly, or it might have picked ONA 0 to 2, 0 to 2, 1, and then gotten stuck needing to backtrack all the way. And greedy best first search, which only looks at the heuristic, would have seen that 0, 1 and ONA 0 both have an H cost of 30. It would have just picked one, say 0, 1, and followed that path, never knowing if the path through ONA 0 was cheaper to get to. A* is smarter. It saw that both paths, 0, 1 and ONA 0, had a total estimated cost F of 40. It is intelligently exploring both routes around the obstacle simultaneously, because its f of n function correctly identifies that both paths are, at this moment, equally promising. It doesn't prematurely commit. It lets the costs speak for themselves. This is the balance of g of n and h of n in action. So A* is smart, but how do we know it's always right? How can we guarantee it finds the absolute shortest path, not just a pretty good one? The answer lies entirely in the quality of our heuristic. For A* to be optimal, its heuristic must be admissible. This is a simple but powerful rule. An admissible heuristic never overestimates the true cost to get to the goal. It must always be optimistic, or at best, perfectly accurate. The Manhattan distance we used is admissible because it calculates the distance assuming no obstacles. The real path can only be that long or longer. To understand why this matters, imagine you're booking a flight and you ask two travel agents for the travel time. Agent A is admissible. They always quote you a time that's less than or equal to the actual flight time. They might say 4 hours. And the flight ends up taking 5. Agent B is inadmissible. They overestimate, saying 8 hours for that same 5-hour flight. Which agent would you trust to help you find the best option? You'll eagerly explore the paths suggested by Agent A, because their optimistic estimates encourage you to check potentially great routes. You might ignore Agent B's suggestions entirely, even if they lead to the best flight, because the initial estimate was so discouragingly high. This optimism is the mathematical key to A* guarantee. Because the heuristic h of n is an underestimate, The total score f of n equals g of n plus h of n is also an optimistic underestimate of what the final path's true cost will be. This ensures that S* will never prematurely finish on a suboptimal path. If a truly shorter path exists, there will always be a node on that path, still sitting in the open list with a lower F score. This lower score acts as a mathematical promise of a better alternative, forcing the algorithm to explore that path before it can declare victory on a more expensive one. For the truly curious, there's a slightly stricter condition called consistency or monotonicity. A consistent heuristic is one where, as you move from a node to its neighbor, the heuristic cost doesn't drop by more than the actual cost of that single step. It essentially means the heuristic gets progressively more accurate as you get closer to the goal. All consistent heuristics are admissible, and they make S* run even more efficiently by ensuring that once a node is expanded, the path found to it is the best one. This reveals a beautiful trade-off between speed and optimality, which is a common misconception. It's easy to think that any heuristic is fine, or that you always want the fastest one, but let's look at the extremes. Consider a heuristic h of n equals 0 for all nodes. Is this admissible? Yes, the true cost is always 0 or more. It never overestimates. But what algorithm is a star with h of n equals 0? The formula is f of n equals g of n plus 0. It's just uniform cost search. It's optimal, but it's blind and slow. Now consider an inadmissible heuristic, one that lies and overestimates. S*, driven by this huge incorrect h value, will act just like greedy best first search. It will be very fast, but it will have zero guarantee of finding the shortest path. So, the more informed your admissible heuristic is, the closer it is to the true cost without ever going over, the faster a star runs while still guaranteeing optimality. This is the sweet spot. The algorithm designed for a shaky robot in the 1960s now silently powers our world in countless ways. Its applications go far beyond what its creators could have ever imagined. The true power of S* comes from its abstraction. A node can be any state, and cost can be any metric, whether it's distance, time, or fuel consumption. The most intuitive example is GPS and navigation. Your map app represents the road network as a graph, where intersections are nodes and roads are edges with a cost based on distance or travel time. The heuristic is often the straight line as the crow flies distance to your destination. A star then calculates the best path, and with real-time data, it can even change the cost of roads on the fly to route you around traffic. In video games, almost any time an enemy or ally navigates the world, S* is likely at work. It helps non-player characters, or NPCs, find the player, move to cover, or follow a patrol route, all while avoiding walls and obstacles in a way that looks intelligent and believable. The modern economy runs on logistics and robotics. S* and its variants are crucial for optimizing routes for delivery fleets, saving millions in fuel and time. Inside massive warehouses, autonomous robots use S* to navigate the aisles and retrieve products with incredible efficiency, forming the backbone of e-commerce fulfillment. And in network routing, when you send an email or load a web page, your data is broken into packets. Network routers use pathfinding algorithms to send these packets across the vast graph of the Internet, while many core Internet protocols use simpler algorithms like Dijkstra's, which, as we now know, is just a star with h of n equals 0. A star is used in specific applications to find efficient point-to-point routes in complex networks, minimizing delay and ensuring your data arrives quickly. We started today lost in a dark maze, trying to find our way with simple blind rules. We then found a glimmer of hope. a heuristic that gave us a sense of direction, even if it sometimes led us astray. Finally, we arrived at S*, the algorithm that masterfully balances the reality of the path taken with an optimistic guess about the path ahead. Remember that golden formula, f of n equals g of n plus h of n. It's more than just an equation, it's a strategy. It's the wisdom of Dijkstra's algorithm combined with the ambition of greedy search. It's the perfect blend of realism and foresight. From its humble beginnings inside a wobbly robot named Shaky, S* has become a cornerstone of artificial intelligence and computer science. It's a beautiful example of how an elegant, powerful idea can hide in plain sight, quietly and efficiently finding the best path forward in a complex world. We've now built a solid foundation for how an AI can find a path. We've given it a map and a strategy. But what if the problem isn't a path? What if the problem is knowledge itself? How does an AI know that Socrates is a man and all men are mortal? And how can it reason with those facts to conclude that Socrates is mortal? In our next episode, we move from searching to knowing. We will explore the fascinating world of knowledge representation and logic. We'll ask, how do you store human knowledge in a way a machine can understand and, most importantly, reason with? This will be our final pillar of classical AI before we pivot to the revolution that changed everything: machine learning.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.